So while this is hopefully setting itself back up, yes, there it goes. Let me take this opportunity to thank Carmen and the other organizers for inviting us over. It's wonderful to be here, what is actually for me my very first visit to Bulgaria. But of course, Carmen and I have had several interactions over the past couple of years or so. And it's really great to see that now we are here discussing LOFAR with you all. Scientists, I understand, mostly, perhaps a few others. And so in an audience like this, it's always very difficult to know how to pitch the talk. So I hope those of you who will think that my talk is shallow will forgive me, as well as those who might occasionally get lost in some of the details. It's really a challenge to know where to go. So I will try to tell you a little bit about LOFAR, and then, as you see in brackets there already, about some plans for the future that also Carla Baldovina after me will talk about in a lot more detail. So LOFAR, as has been already alluded to, is a true pan-European distributed infrastructure. There are now 9 member countries in the International LOFAR Telescope, and you see them sketched out here. It's an array of very simple radio dipole stations. The smarts in this kind of facility is largely not in the very front end of it where the antennas are, but it starts immediately thereafter with all of the electronics that are in each of the 52 antenna stations, and then also very much in the data processing that follows after. We operate in what are the lowest frequency bands that are accessible below the ionosphere on Earth. If you go below 10 megahertz, really, you should be going into space. And that is the window in which, actually, surprisingly, radio astronomy has not ventured for a while. Some of the historical radio astronomy was done there in the 1950s and 60s, a bit in the 70s. But radio astronomy there was hard, in some cases still is hard, because in fact, indeed, the Earth's upper atmosphere, the ionosphere, sometimes disturbs the signals so much that you need today's modern data processing to get anywhere with imaging the sky that's beyond our atmosphere. So we have a lot of on-station data processing in each of these 52 stations, and we have central processing that I'll tell you about. One of the great things that you can do when you're a mostly electronic telescope is you can respond very rapidly to events that go on in the sky, transients as they are called. And also we very much continue to use LOFAR as a pathfinder for technology. Just as one example, this is very data-intensive astronomy. LOFAR generates in its archives 7 petabytes of data per year. So it starts, as I said, at the very front end where there are dipoles, and they don't actually look all that impressive. There are two generations, two types. One for the frequency band below the FM radio band, 30 to 80 megahertz or 10 to 80 megahertz. Very simple design, very many of them, 96 per station, 52 stations. And then above the FM band, 122 to 140 megahertz, you have tiles of 4x4 antennas, again, 96 per station. And so you get a lot of sensitivity from having a lot of antennas. And these antennas are more or less sensitive to the whole sky all at once. So in the center of LOFAR, which is in the Netherlands, in the northeast of the Netherlands, we pack a lot of these together very closely. You see the tiles there as the black spots, and then the smaller dots sprinkled around are the low-band antennas. And you see several other stations, as they're called. This is a separate station. And there is one in the upper right-hand corner as well. And then they spread out from there, literally into Europe. Choosing which direction to look at on the sky is done digitally. The The patterns here show the instantaneous sensitivity of an individual dipole, which is very broad across the sky. That's what the sketch is showing. It shows you that when you then combine the antennas from a station, you get much narrower sensitivity on the sky, but it's much higher per area that you choose to look at. You can choose to look at multiple areas all at once. It's simply a question of duplicating the signal electronically and processing it in parallel. And then if you start adding up more and more antennas in this tied array, your sensitivity grows and grows. And at the same time, your ability to distinguish individual features on the sky increases, your resolution on the sky increases. So the data flows from these individual antennas on the left-hand side of this sketch into the processing cabinet on the station, where the analog signals are first of all digitized, filtered, and then this process of beamforming takes place, where you select your area of the sky or multiple areas of the sky that you want to look at simultaneously. And then the data makes its way to the central processor, which is located in Groningen in the Netherlands. There's also a very interesting feature that LOFAR has, which is written on the right-hand side there, this transient buffer. This is a cyclic data buffer that stores data for a number of seconds, so that if a transient goes off, there is some flash in the sky, you actually have the historical data some seconds before it happened, and you can freeze the buffer and you can find out, was there any activity just in the little bit of time prior to that event going off, and you can then turn your beamforming on that part of the sky and discover what was happening there. The trigger can be internal to LOFAR. You can discover a radio flash. You can also get your trigger externally from, for example, an X-ray satellite that has discovered an X-ray flash, and then you can see if there's a corresponding radio feature to it. So then, indeed, signals get collected from all over Europe, and I show you here, of course, very roughly where we would like to have that one Bulgarian station lie. And you see that it's an interesting place because the imaging capability of a network like this depends on having what the specialists call UV coverage. You need to have a variety of spacings between stations. You need to have a variety of orientations between stations across Europe. And you see that having the southeast corner of Europe covered would bring longer baselines, larger UV spacings, meaning finer imaging resolution that you could have on the sky. You could see finer detail of objects that are in your celestial images. And especially, it goes a little bit further south, and that's also a very good feature to have, because as you go to image objects that are closer to the equator, then with the current network, we lose some of that imaging resolution, and having stations further south will definitely help there. The data makes its way then controlled from the control room at ASTRON in Dwingelo, the Netherlands, the Netherlands Institute for Radio Astronomy. They control all of the stations all at once. The data flows to this so-called correlator data center in Groningen, where the data streams are cross-correlated or are otherwise combined in various ways in order to produce images or other radio data, and then make their way to archive sites. And again, I stress 7 petabytes per year is a prodigious amount of data to want to store, and it's done at the moment in 3 different data centers, one in the Netherlands, one in Germany, and one in Poland. And actually, I'm fairly actively looking for other data centers that might be interested in participating in that load, because the plans we have for the future will only have that data rate expand. Here's our current storage. Since we started operating, we're now above, well above 40 petabytes in that archive already. In the archive, from the archive, and in fact also on the way to the archive, we have developed a number of science analysis software pipelines that produce either images or, for example, for pulsars that produce time series. Also for some of the solar work, solar dynamic spectra can be produced in that way. And this transient buffer capacity that I was mentioning can be read out. We are developing dynamic scheduling, which is meaning that you have a whole range of objects that are ready to be observed, and you choose the one that for which the conditions on the spur of the moment are the most auspicious, or you switch to some transient phenomenon going on. These pipelines, they are very, very sophisticated. This is really where the smarts is in a lot of the data processing. Just as an example, this is a raw image after the standard technique that high-frequency radio astronomers apply, which is called self-calibration. That's where you try to remove variations in the phase of the radio signal due to various instrumental and atmospheric effects. Frankly, this is a failure. And it's only when you become more sophisticated that you get an image on the sky that is usable at these frequencies. This is a technique called direction-dependent calibration. It means that you need to solve for the transmission through the ionosphere at very many different points on the sky all at once. It took a number of years and a number of very smart people to develop this technique. We now have this technique very well tuned for the higher bands of LOFAR. In the lower bands, we still have a ways to go, and this is one of our ambitions for the coming decade under LOFAR 2.0. And again, that will be a combination of using more compute power, more smart electronics, and more smart minds to get there as well. We really need to get access to some of the best minds of Europe as well. So then what do we use this for? LOFAR was already mentioned. It's very versatile. Astronomy in general indeed touches on very many different other disciplines. The user community of LOFAR also spans not just those 9 countries that are now formally a part of the International LOFAR Telescope, but also wider across Europe and the world. And of course, different groups specialize in different aspects of this whole gamut of science that I am going to very briefly touch on here. So there are opportunities certainly for new groups to come in, groups that have their own science interests and may be inspired by some of the examples I show in thinking about how low radio frequencies can enrich their own research. I don't think there's any country in Europe where all of the research topics that I show here are handled all at once. Mostly groups will specialize, although of course the Netherlands being the initiator of LOFAR and still the leading country in LOFAR probably has the largest community. So let me go through a few of these examples, and what I will do is I will go from the early universe, the faraway universe, closer to home gradually. This is one of the flagship research areas for LOFAR. This is trying to detect statistically what's called the epoch of reionization after the so-called dark ages, when the Big Bang had cooled, the remnants of the Big Bang had cooled down. The universe was neutral, and then at some point the first coagulations of matter started to shine, and those very early galaxies, very early stars, then lit up the universe and reionized the hydrogen. And it's that signal which happened over a range of time, and that's exactly what people are trying to look at. What time period did this actually cover, this reionization of the hydrogen in the early universe, that we're trying to get a statistical handle on. The technique used is the fact that that hydrogen, when it's neutral, emits at a very specific frequency, which at rest falls at a frequency of 1420 megahertz. But as you go to early times in the universe, because of the Doppler shift, goes to lower frequencies and falls in the LOFAR band just at the epoch of reionization. It's a very, very difficult measurement to do. It needs thousands of hours of coherent integration time. You need to filter out lots of disturbing effects, both from the instrument, but also from foregrounds in the universe, literally foregrounds then in the universe. The detection hasn't been made yet. This is one of the recent papers that was published, showing that the groups are well underway to understanding all the systematics. And well, we look forward to getting more results from this in the next couple of years. The probably second largest project going on at the moment is the LOFAR 2-meter sky survey, LOTS. It's literally finding lots of different objects in the universe. It's proceeding gradually to observe the whole northern sky. It started at the higher declinations, but is now moving its way south. The diagram here shows you a plot of sensitivity as a function of frequency, and it shows you that LOTS is in a very sweet spot. Its sensitivity is outclassing that of most of its rivals in astronomy, certainly in low-frequency astronomy. And the lines you show there show that for many objects that will emit with a given spectrum, that is distribution of brightness over frequency, you are comparing very well to some of the higher frequency surveys as well. And so this is aimed at finding objects again in early times, but not quite as early as the epoch of reionization. High redshift radio galaxies, how do they form? How many do you find at various epochs? What do they look like then? When are they well formed? When are these massive galaxies really in the shape that we find them in the modern universe? When do their black holes form? What is their star formation rate? Were there periods in the universe when star formation in these objects happened at a higher rate or a lower rate? And of course, as always, you are looking for the unexpected. When you get millions upon millions of objects, there will be a few that surprise you, that point the way to unknown physics, and that pose interesting future questions. The first data delivery from LOTS is out, publicly available. Further releases will follow in the coming years. A few examples of the kinds of things that you then do. You start to see the distribution of gas that, by the way, radio emission in general is often good at showing not so much what is called thermal emission, so directly hot stars or whatever, but is good at showing what is called non-thermal emission, which has to do with relativistic electrons, with plasmas, with shocks in the universe, very high energy phenomena. This gas, it turns out, in many galaxies and many clusters of galaxies, spans a much larger extent than what you see optically. The false color images are the radio emissions, radio images, and they show you much larger structures than if you look at the optical galaxies or the optical clusters. They show you interactions. They show you then, by extension, the formation history of these objects and the way they interact with each other over cosmic time. That's what these images are conveying here. You can also dig down, drill down more deeply into individual objects, as is shown in this diagram, where you make full use of the International LOFAR telescope, the array of stations that allow you to get to subarc second resolution, and you find it isn't showing up particularly well, but for example, in the top left-hand corner here, you see that in this galaxy M82, there are a few very bright spots, which are individual supernovae and stars that have recently exploded. On the right-hand side, you see some of the black holes emitting relativistically moving plasma jets, and these produce radio emission. You can study them in great detail. The contribution of low frequency there is that typically these were first studied at higher frequencies where the shocks leading to this kind of gas produce a fairly simple synchrotron power spectrum, but at lower frequencies you see the energies of the electrons as they cut off, or you see the effect of so-called free absorption in some cases, the more neutral gas that is also present in these objects and that is sometimes stifling the outflow of the jets. You can do very detailed studies by having a range of radio frequencies, including LOFAR. You can also study the magnetic field structures. This is coming now a little bit further home to our own Milky Way galaxy, where in overlay to a background radio source on the right-hand side, you see a number of filaments in the galaxy that that have different magnetic field configurations. And people are trying to understand how it is that our Milky Way galaxy can have such a complicated structure in its magnetic field. You are helped by backlighting from the extragalactic sky to understand the structures there. Also in our own galaxy, one of the most famous supernova remnants, remnants of an exploding heavy star, Cassiopeia A, being studied in great detail here. The images on the right hand show you the so-called spectral index, the difference between the brightness at various radio frequencies, again giving you physical information about shock strengths and the energies of the particles that you see there. The lower part of this diagram shows you that you can, in fact, not only study hydrogen gas. This is to do with atomic and molecular gas, all of which also have telltale signature spectral line emission, as it's called. And you can study the velocity structure of these clouds in great detail by seeing how these lines are broadened by the velocity of the gas, and in fact at what velocities they all fall. So these are on the right-hand side comparisons between molecular lines and also recombination lines. Moving again a little bit closer, here you see the detection of a T-Tauri star, where again the question being asked is, well, this T-Tauri star is producing an outflow, and the outflow you want to understand what its physical properties are by looking at the lowest radio frequency emission and how that shows you a turnover in the spectrum. Moving to transients and variables, I always show the one on the left because it was my original PhD thesis subject, SS433 and W50, even back 35 years ago or whatever it was. This was an interesting object, but it still is. There is an almost one-to-one correspondence now between images shown at a factor of 10 in frequency apart, and you can do really wonderful studies about how this object is blowing a bubble into the interstellar medium of our Milky Way. The flash on the right-hand side, I guess, speaks for itself. It's that kind of transient source that LOFAR is constantly on the lookout for. Here's a bit of pulsar science, just a little bit. There's a lot of pulsar science being done with LOFAR. It shows you that as you go through different frequencies, you get information about how the spectrum of this pulsar changes, and therefore the emission cone can be studied in great detail. You get an understanding of the astrophysics of how pulsars actually pulse here. Coming to our sun, I will not dwell on this because there are several speakers after me who will talk about the wonderful ways in which solar radio bursts can be imaged and all sorts of other applications to the sun and its immediate surroundings, the heliosphere. But having access to a range of frequencies here is crucial to understanding how these violent phenomena on the sun work. Talking about violent phenomena, there are lots of very poorly understood issues about the highest energy particles that we can detect from Earth, high energy cosmic rays they're called. LOFAR has a unique ability to study their energies and their directions of origin because of the antenna arrays that we have, where you can actually see the footprint of a radio flash originating when one of these cosmic rays hits the upper atmosphere, produces a radio shower, and you can you can derive the effects the properties of these cosmic rays. Talking about radio flashes and such, this is almost literally a radio flash. These are studies of lightning occurring over the northeast of the Netherlands in this case, that we never thought we would be observing, but it turns out that geophysicists in fact find this very interesting. They can get access to resolutions, temporal resolutions that they never dreamt of before, and also they can study the discharge in of the lightning flash happening with great detail. So this led to a Nature paper very recently. All in all, again, a very big range of science being handled. We are tracking what our papers are mostly based on. You see, extragalactic is big. Pulsars and transients, like I say, is big as well. There are growth areas. Solar at the moment is definitely a growth area. And so is exoplanets. We have great hopes for the coming decade, when we will be upgrading the instrument. I will not dwell on this at all, because Carla will be saying more about it. But we are upgrading the instrument. We will make use of most of the existing hardware and algorithms and the brain power of the collected community now. But we're on to bigger and better things, the lowest frequencies, the highest resolutions, meaning more international stations as well. And its versatility will also increase. We want to be able to do more simultaneously. And so in all of that endeavor, of course, what we're here to talk about today also is that you, as the Bulgarian community, would be very welcome to join us. Thanks again for your attention and for the invitation to be here today.